Do 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 do. Welcome to video 2 of week 3, where we're going to talk about moles. And despite the fact that the pictures are of moles, the animal, or what I think looks like a star-nosed mole from Avatar: The Last Airbender, the show, not the movie. The show was great. The movie, not so much. Despite the fact that there's pictures of these moles here, we're going to talk about what a mole is in chemistry. So buckle up and here we go. Okay, so what is a mole then? Because of the very small size of atoms and molecules, chemists use a unit called the mole to represent the number of atoms, molecules, or particles in a sample. So basically what we're saying is that because atoms are so tiny, it makes no sense to talk about single atoms or 10 atoms or even 100 atoms. It makes sense to talk about a whole lot more than that. And a mole is actually defined as a number of atoms in exactly 12 grams of carbon-12. So if you have 12 grams so a dozen is a useful number that we all know. A dozen you will have things. 1 mole of atoms. So less what does that even mean? My mother-in-law just said she wasn't aware of just a useful number. So here's some other useful numbers. So 1 gross is actually a dozen. So 12 times 12 is 144 things. So you can feel free to use that number. You can say, hey, I feel like I've been quarantined for 1 gross amount of days. And most of your friends will think you're just talking about a disgusting amount, but you will secretly know you're talking about 144 days. 1 decade of years is 10 years. That's a pretty common one. A century is 100 years. So just like dozen or gross or decade or century are useful numbers, in chemistry, a mole is a useful number. And a mole is a lot bigger than any of these. It's 6.02 times 10 to the 23. So that's 6 and then a 0 and a 2 and 21 more zeros after it. That's a lot of things. We also refer to it as Avogadro's number. So if I had a mole of oranges, I would have 6.02 times 10 to the 23 oranges. If I had a mole of diamonds, I would have 6.02 times 10 to the 23 diamonds. If I have a mole of atoms, I have 6.02 times 10 to the 23 atoms. If I have a mole of molecules, I have 6.02 times 10 to the 23 molecules. That's going to be important moving forward. Sometimes you'll hear mole referred to as a chemist's dozen because it's such a useful number. So you can see here we're going to talk about molar mass, so we needed to know what a mole was first. So when we talk about atomic weight or average atomic mass, we measure it in AMU per atom. This is the number on the periodic table. So this is what you're used to doing. So if I asked you, what's the atomic mass of 1 atom of copper, then you would find copper on your periodic table. It's number 29, and it tells us its atomic molar, or its average atomic mass is 63.55. That's the number at the top right. And the unit here would be AMU per atom. So each atom would have a mass of 63.55 atomic mass units. So we don't usually use this notation. And because these atoms are so small, what we can actually do is talk about molar mass. Molar mass is the mass of a mole of that substance. So this number, 6.02 times 10 to the 23 atoms or molecules of that substance. It's the same numerical value as the atomic weight up here, but we measure it in grams. So the average atomic mass of 1 atom of copper was 63.55. The molar mass is also 63.55, but its units here are grams per mole. And you'll actually see that written on your periodic table in the legend, but it'll say G/M. G is for grams. MOL is short for mole, which is only getting rid of 1 letter, but it's still shorter, so we're going to go with it. So this is saying if you had 6.02 times 10 to the 23 atoms of copper, together they would weigh 63.55 grams. And this is why we love doing that. This may sound confusing at first, but we love the mole because the number of molecules in a sample can be calculated using the sample's mass and the substance's molar mass. So we don't usually talk about 1, 2, 10, 100 atoms. We talk about 1, 2, 10, 100 grams of a substance. So we're talking about many more than just atoms. We're talking about moles of atoms. So this said the substance's molar mass. So what is molar mass? Well, it's the mass of 1 mole of a substance. We talked about that just a minute ago. The molar mass of elements is found on the periodic table. We also talked about that. So here's just another example. Calcium, you look that one up. It's 40.08, and we put in units here of grams per mole. However, how do we find the molar mass of a compound? Because we are not always just dealing with elements. Sometimes we're dealing with compounds. And we calculate them by adding the molar masses of the elements in the compound. So you just basically are adding them all up. So here's how we would do that using an example. Calculate the molar mass of barium nitrate. So the first thing we need to do is write the chemical formula. So barium is Ba, nitrate is NO3. Let's make sure that we balance this. Barium is going to have a 2 positive charge. Nitrate has a 1 negative. So in order for this to be balanced, we're going to need 2 nitrates. It's going to be BaNO3 2. And just for good measure, we could look up nitrate on our solubility of ionic compounds. We would remember, hey, anything with nitrate is going to be highly soluble. So if we put barium nitrate in water, it would dissolve and it would be aqueous. All right, let's get back to molar mass though. So we've written the chemical formula. Now we multiply the atomic weight of each element by the number of atoms of that element present in the compound. So we're dealing here with barium, we're dealing with nitrogen, and we are dealing with oxygen. So the atomic weight of barium is 137.33, and we only have one number of atoms of it, so we could put times 1 equals 137.11. Nitrogen, we look it up, it's 14.01. And how many nitrogen do we have? 1 times 2, we have 2. So that gives us 28.02. And oxygen, we looked that up, it's 16.00. Those zeros are significant, so don't forget them. And we have 3 times 2 is 6. So 16 times 6 gives us 96.00. So we've got all of those. Now number 3, we just add these all together and use grams per mole as the unit. So we have 137.33 plus 28.02 plus 96.00, and when we add those up, we get 261.35 grams per mole. And that is our molar mass of barium nitrate. I'm going to do just one more example here. Let's skip over water. Let's do aluminum hydroxide. So the way I would write this out would be, rather than writing them all separately like I did before, here's probably what I would do. I would just go with aluminum first, which has a molar mass of 26.98, plus we have 3 oxygen, so we have 3 times 16.00, plus we have 3 hydroxides as well, so 3 hydrogen, I should say, so 3 times 1.01. And then I would just do that all in one step on my calculator. So I have 26.98 plus 3 times 16 plus 3 times 1.01. Make sure you're following order of operations, or your calculator is. If you get it all right, you should get 78.01 grams per mole. I won't do the calculation here for you, but for water, it's 18.02 grams per mole. Here's some practice for you. The answers are over here on the side, so try them. Make sure you can get the proper answers. I want to take a look just at question number 8 here. This is a hydrate, copper sulfate, pentahydrate. So remember, we have water loosely attached. A really common mistake, so if you don't get this one correct, is this. We're used to that notation meaning multiply. We're not going to multiply here though. This means you have copper sulfate and 5 molecules of water attached to it. So this, when you're calculating molar mass, is going to mean add. So you're basically going to add the molar mass of this and the molar mass of 5 molecules of this together to get what the final answer should be. So please don't multiply here. Common mistake. All right. Let's look at one other thing here as our intro to moles, and that's converting between these masses and moles that we were just talking about. So to work with chemical reactions and balanced equations, you need to be able to convert a mass to an amount of moles. And this is the formula that we're going to use. You're going to use this formula for the rest of your chemistry career. You're going to have to memorize it. You'll use it in grade 12 chemistry as well. It's N equals M over M, or you'll hear me say N equals little m over big M. So what do all these things mean here? So what is N, what is little m, and what is big M? So little n here is the number of moles. Little m is our mass of our sample, and this is going to be in grams. And big M is molar mass, and the units of molar mass are our grams per mole. So this is the formula that we're going to use. We might have to rearrange it. Basically, we're going to be asked to convert between these two. You're going to be able to find molar mass based on the masses given on your periodic table, and you're either going to be given a mass of a sample or the number of moles in a sample and be asked to convert between the two of them. So here's an example. How many moles is 4.91 grams of sodium sulfate? So the first, if we're going to use this formula, N equals little m over big M, we are given here 4.91 grams. This is little m. This is a mass. We're asked to find how many moles. We're looking for N. And so the other thing we need to know is big M, molar mass. So that's what we have as first step. Find the molar mass. So for sodium sulfate, we will have 2 times sodium, which is 22.99, plus you could put 1 times sulfur, so 1 times 32.06, plus 4 times 16.00. And let's see if I can use my calculator properly here. Plus 32.06 plus 4 times 16. Check my math to make sure I get these right. 142.04 grams per mole. Step number 2, use the formula to find moles. So N equals little m over big M. We don't need to rearrange anything because we're already isolating the number of moles, little n. So our little m is 4.91 grams divided by big M, which we just calculated as 142.04 grams per mole. If we take a look at our units, grams are actually going to cancel out, so that's great. And using your calculator wisely, you can just put in 4.91 divided by, and if your calculator has an answer key and you press it, it should put in the answer to the last calculation you did, which was probably getting the molar mass up here. So when I do this, I get 0.03456.7. I must have chosen numbers to make me do that. ... Always look to significant digits. 4.91 has 3 significant digits, so we should round to 3 significant digits. That's the 5 right here. So we'll have 0.0346, and our units are moles. Does that answer make sense? Does it make sense that we would have less than or only 3/100ths of a mole? Yeah, if the molar mass, so if 1 mole has a mass of 142 grams, and we only have roughly 5 grams. That's a very small portion of a mole, so this makes sense. What about if we go the other way? How many grams? So now we're looking for little m in 2.23 moles, so this is N, of H2O. So we have our formula, N equals little m over big M. We're asked to find how many grams. We want to rearrange for this. So what do we do to rearrange for little m? We're going to multiply by big M on both sides, and we will have little m equals Nm. So we need to calculate big M, our molar mass of H2O. So that's 2 times 1.01 plus 1 times 16.00. You don't have to pick up a calculator for that. This is 2.02 plus 16 gives you 18.02 grams per mole. So this is pretty easy. So the number of moles was 2.23 moles times 18.02 grams per mole. And you can again see our units canceling out, moles on the top, moles on the bottom. We have a final unit just of grams. So 2.23 times 18.02 gives me a mass of 40.1846. Again, round to significant digits, so we were given 3 here, so we should round to 3. So this would be 40.2 and include our units of grams. So 2.23 moles of water is going to be 40.2 grams.